Okay, Bismillah Rahman Rahim. Welcome to the class. So today we are going to take the sixth lecture of our course, and in this lecture we are going to talk about the inelastic single degree of freedom systems. Okay, so till now we were talking only about the linear elastic systems, the single degree of freedom system as well as the multi degree of freedom system, but in all cases we assume that the system is behaving linearly and elastic when it is subjected to ground motions. But anyway, we will see that in reality, most of these buildings, when they are designed for base shear smaller than the peak base shear in the structure, computed under the assumption that it is linear elastic. So let me just give you an example. If you look at the force and deformation behavior of a structure, say this is on x-axis, we have the deformation that's represented by displacement u, and here we have the force, the resistance of the system represented by the Fs. So during a linear response, you will see that the force and displacement, they are linearly related. So there will be a straight line between these two. Okay, let me show also this dash line. And this will have some particular natural vibration period. Let's represent it by T naught, or you can also represent it by T1 to represent the fundamental vibration period, or the vibration period of the first mode of the system. For a single degree of freedom system, this vibration period is just a single value, so you can just represent by T or T naught. So during an earthquake, if you assume that the behavior of the system is linear and elastic, the force deformation behavior is straight, and there's a single value of the vibration period. And for that vibration period, you can compute the acceleration that this single degree of freedom system will experience, the response acceleration, as well as you can calculate and from that acceleration, you can calculate the force, elastic corresponding force for that acceleration, as well as you can calculate the corresponding deformation for that. Okay? So, so if we use that, this is the elastic behavior. This system will experience a base shear. There will be, let's try that this is elastic. So this V elastic will be equal to the Fs for that T naught. But in reality, the structure has always a force deformation behavior, which can be idealized as, in most cases, as elastoplastic. So this is the elastoplastic behavior. And it is known from the past many experimental work that the actual force deformation behavior of the structure system is not linear, but it is rather has also uh, an inelastic behavior or a non-linear behavior, which can be idealized as an elastoplastic. This is the corresponding linear elastic system. And in most cases, the buildings which are designed in according to the code, they are designed for a V for a force. Let's say that is represented by V design, and this design base here is always less than the V elastic. Okay, so whenever you design a structure where the force is less than the V elastic experience in an earthquake if the a system is entirely behaving elastically. So obviously, when V is more than V design, it will cause the system to behave inelastically. Okay, there will be always a behavior that will be represented by the actual force deformation behavior of the system. Let me just go to this figure here. Okay, so what you see on this example figure is that there is the elastic design spectrum that you can see. Okay, this one that start from zero point 0.4 G. Okay, there's a straight line. Then you can see that there is a plateau of this plateau branch of the acceleration response spectrum, and then you can see that this decaying branch of the acceleration response spectrum. In this kind of spectrum, you can draw using the code procedure. In code, there is a procedure given how to construct such elastic design spectrum, and we always need this for the design of structures. So anyway, on the along with this elastic design spectrum, there are other two spectrums given here, this one and also this one, which shows the base shear coefficient. So on y-axis, there's a base shear coefficient where base shear coefficient is equal to the A divided by G. When you divide the acceleration by the value of G, it is converted to the base shear coefficient. So if you remember, normally in code, that V is given as A by G into W. Okay. So if you write the base shear is V by W, you have on the right side is A by G that represents the base shear coefficient. In the new codes, this A by G is represented by CS, where CS is the base shear coefficient or the seismic response coefficient. Okay. Now, if you look at the elastic spectrum here, you will see that the acceleration of these, again, the elastic design spectrum is also in terms of G. So these can be directly compared with the base shear coefficient. And you can see that these acceleration values, the elastic design acceleration values, and remember that these are for the 5% damping, for the linear elastic 5% damping. These values are always higher than these base shear coefficient, you can see. Okay, and the base shear coefficient, there's a way how to calculate base shear coefficient in the code it is given, and always you will see that in CS there is the role of the response modification factor, the R factor, and for some of the building the R factor can be smaller like 1.5, but for the other ductile structure this value can be even higher up to even 8. For example, the steel frame and the special moment resisting frame. But anyway, if you look at the very high value, for example, the 8, you can see that the base shear coefficient is very, very small. It may be something like zero point 0.8 or maybe uh, zero point 0.1 or it may be like 0.155, 0.15 and so on, and up to the let's say zero point 0.7, 0.65 W for a structure which are less ductile. But in any case, if you compare these values over a range of these vibration period, you will see that the spectral acceleration, the elastic spectral acceleration are quite larger than these base shear coefficient value. So what is happening? This implies that the building design for core forces would be deformed beyond the limit of linear elastic behavior. So it tells us that the structure will essentially behave non-linearly because the force for which we are designing it is more or less than the force which is actually experienced in case of the linear behavior. So what is the problem? The problem is that the structure would be damaged when subjected to ground motion that is represented by the design spectrum. For example, if you take any accelerogram, any ground motion that is represented by this design spectrum, for example, the spectrum compatibility or matching that we do. So if you take an accelerogram and you match it to the design spectrum, when you input that accelerogram to the structure will behave non-linearly, inelastically, and it will get damaged. For example, if you are doing a shake table testing for structures, when you input that accelerogram to the test model, you will see that the model will get damaged because the resistance or the Bayesian coefficient is much less than the demand for an elastic system. So the challenge to the engineer is to design the structure so that the damage is controlled to an acceptable degree. So as an engineer, our job is not to is not to avoid damage. It will happen, but the challenge is to bring it to an acceptable value. So so the structure design is obviously not successful if the damage is too severe to be repaired economically, or if the structure collapses. So if you design a structure and after the earthquake it is collapsed, so obviously it's a failure. Or if you design a structure, it is severely damaged, it is not repaired economically, so again that is not a success, it's a failure. So therefore the response of structure deforming into their inelastic range is of central importance in the earthquake engineering. So let me just give you an example. Is, for example, this is one of the case, the Olive View Hospital that was damaged in the 1971 San Fernando earthquake. It was a two-story structure, and you can see that the lower story is completely collapsed. So you can see a story mechanism, and you can see that the lower story is completely crushed. So this kind of behavior is obviously not acceptable for a code-based design. Uh, this is obviously a collapse, and everybody understands this. This is another example of a structure that was subjected to 1994 Northridge earthquake. And you can see that there are damages, the severe cracks that you can see here, this diagonal cracks, these, this, and this, so on. So you can see cracking, severe cracking of the columns. And you will also see that at this story, you can see that there is certain shortening of the story because of the column failure. And you can see that those windows are buckled. So even behavior like this cannot be repaired economically, because for a medium rise or high rise structure, repairing this kind of damaged structure is impossible, because you cannot use jacks to lift the structure and then repair it, and so on. So it's quite challenging. So these kind of behavior is obviously not acceptable in an earthquake. So the design has to be in such a way to provide a system with enough strength as well as ductility. And for this, we will talk about how we can select strength, how we can select an appropriate ductility for a structure system in order to provide the um, the behavior that as an engineer is acceptable to us. And also, sometime for an existing structure, it is important to understand how this will behave in the future earthquake. So for those understanding, it's important to understand the inelastic behavior. Let's talk about the idealized inelastic system. Okay, so since the 1960s, thousands of laboratory tests have been conducted to determine the force deformation behavior of structural components for earthquake condition. So I will mention that the since the 1960s, a lot experimental tests have been conducted on structure to obtain the force deformation behavior. Okay, so the experimental results show that the cyclic force deformation behavior of structure members or the assemblages of members or small scale models of structures in full scale structures depends on the structure material and on the structure system. So that force deformation behavior depends on materials and system, the structural system, which means that, for example, if the structure system, whether it's a load bearing system, it's a wall system, it's a dual system, it's a frame system, it's a brace system, and the material, whether it's concrete, whether it's uh, steel, whether it's masonry or any other type. So depending on the material and depending on the structure system, the force deformation behavior can be different. So it mainly depends on the material as it is on the system. But there is one fact that all these force deformation plots show the hysteresis loops under cyclic deformation because of the inelastic behavior. So you will see that majority or almost all of these real structure, they behave inelastic. They show inelastic behavior. Okay. So how you can see that there is inelastic behavior. For example, if you look at their cyclic response, for example, if there is a displacement on x-axis and a force on a y-axis, when you push that structure back and forth, let's say if we have this structure, okay, so you will see that it behaves something like this. So it's not a linear behavior of force and displacement, but rather it has a certain loop. The loop which is called is the hysteresis. Okay, so this implies that the behavior of these structure system is inelastic. Idealized version of these force deformation relations, which are appropriate for the structure material structure system, it have been used in many computer simulations when you are looking at the earthquake response of the single degree of freedom system. So in many computer programs, the idealized behavior of various structure system is already known to us. For example, for steel, majority of the people use bilinear behavior. For reinforced concrete beam, the Takeda type response is used. For the reinforced concrete column, it's a modified Takeda, and there are flagship is used for the rocking system, and there are so many hysteresis response which are available in a number of computer programs. Okay, the elastic stiffness, let me just write here. If you look at the fact that in the previous example we showed a behavior something like this for a force. Okay? Displacement and force, which is basically representing the backbone envelope of the hysteresis response. If you have the hysteretic response of a system, you can develop the backbone curve uh, by taking the peaks of the displacement and the corresponding force, and you can idealize them as an elastoplastic system. For that elastoplastic system, the elastic stiffness is represented by K, okay? And the sometime the system may have some post-yield stiffness, we just mentioned here. If the system is perfectly elastoplastic, then let me just write here that this stiffness is alpha K, where alpha is the post-yield stiffness ratio. So for alpha is equal to 0 for elastoplastic system, but it can be more than 0 when the system is bilinear. When it has two branches, one is this elastic and the other is this one, and in that case alpha is more than 0, so it can be 1%, 2%, 10%, 3%, and so on, depending on the system that you are analyzing. The yield strength of this idealized system is represented by Fy, okay, which is basically the point where uh, the force deformation behavior deviate from a linear branch, and the corresponding displacement at that point is Uy. It's the yield displacement of the system. Okay, I think I have seen this here. Okay, so here you see this is a nice plot. Okay, so you can see that this is the yield strength. This is the corresponding yield displacement. Okay, and this can be the idealized linear system, but the actual system is that it yields at the Fy. Okay, and this is the when the yield strength is reached, the system will behave only in the displacement mode. So, like increasing the input demand, the ground motion will only increase the uh, maximum displacement demand on the system, but the force will be constant. So later on, you will see that the ratio of this maximum displacement to the yield displacement is called the ductility. Okay, and the ratio of if naught to if y is a strength reduction, is the yield strength reduction factor of the system. And this is the cyclic behavior of the same elastoplastic system, but just like the structure system, but in a idealized manner. And only the positive response of the system is shown. For example, if in an earthquake it exceeds the elastic limit and now behaving in the inelastic range, uh, upon the unloading, the system unload following this path. Remember that this stiffness is exactly equal to this stiffness. Only difference is that here the velocity sign is negative. Then in the opposite direction, when it reaches the yield strength in the negative side, again it gets and behave a plastic behavior. And once it reach this point, and when the loading is changed, when the velocity sign is changed from minus to positive, it will start reloading. And in the reloading stage, again, the stiffness remain exactly the same as the initial stiffness. So the loading and the unloading stiffness remains equal to the initial stiffness. This is a behavior in which we assume that the stiffness is not deteriorating. So it doesn't happen in a real system, but this is the idealized behavior. And sometimes in very real cases, in a system where the the system, the stiffness or the strength is changing, is deteriorating. So in that case, these cannot be perfectly exactly the same. But anyway, for understanding and for the theoretical background, it's important to understand that these stiffnesses are exactly the same. Okay, and so as I mentioned that sometimes the alpha can be having some particular value, so that behavior, the behavior can be elastoplastic for the idealized case. It can be even with this kind of behavior if we assume this is what is called as the hardening effect. So there is a, let's say, a hardening effect in the structure system when it yields. Okay, and sometimes the behavior can be like this when there is a softening behavior. So softening behavior normally happen in structures which are existing structure where there is a strength deterioration. So it mainly happen in the strength deteriorating structure. Okay, and sometimes this kind of behavior also happen because of the p delta effect. If the gravity on the structure system is quite larger, in that case also the force deformation behavior can have a branch that is having a negative slope. Now, let me just go back here. Within the linear elastic range, remember that within this range, the system has a natural vibration period. So it has vibration period that is represented by Tn. Tn, we know that it is related to omega. That is 2 pi by omega n, or omega n is equal to 2 pi over Tn. You can write that way. And also it has some particular damping ratio. Okay. The most common case that we assume that the damping is 5%. But once the system is yielded at larger amplitudes of motion, the natural vibration period is not defined for inelastic system. So once the system is yielded, then we cannot talk about what is the vibration period of a system because it doesn't remain the same, it shows elongation. But anyway, the concept of the vibration period that we are using is basically for the system which are elastic and for the system when it is in the pre-yield state of the force deformation behavior. Now, for the inelastic system, it's important to talk about the yield strength reduction factor. Yield strength reduction factor represented by Ry in ductility factor. Where ductility factor is represented by yield. The yield strength reduction factor, Ry, is mathematically it can be written as Ry that is equal to F naught divided by the Fy. Okay, where F naught is the minimum yield strength. So if we look at the elastoplastic behavior, this is F naught, and if it is yielded, this is Fy. So the ratio of the F naught, which is the minimum yield strength, required for the system to behave elastically, and Fy is basically the yield strength. So the ratio of these two is basically Ry. So Ry basically define this thing, which is the yield strength reduction factor. If you look at the okay, this is the yield displacement that we know, and this is the sorry, this is the displacement u naught. This is not u, but this is the displacement. This is u. y, which is the yield displacement. You can also write the equation of Ry is u naught by uy, because you can write this simply uh, by looking at the fact that the stiffness of this inelastic system and elastic system, it is the same. So if the system is if the stiffness is the same, you can write the stiffness equation, and you can show that the Ry is also equal to u naught by ui. Okay. The peak deformation or the absolute maximum deformation, which is here, for example, when the system gets yielded, now there is another deformation that will take place, that is represented by the the peak deformation or the absolute maximum deformation, which is that of the inelastic system due to the ground motion. Okay. Now, the ductility factor that we talk about is basically equal to this inelastic displacement divided by the uh, yield displacement ui. Okay. Now, for the same system, it can be shown that the inelastic deformation ratio that is defined by the ratio of the peak displacement or the deformation of the inelastic system to the corresponding linear system displacement. It is related to the ductility factor divided by the strain reduction. Okay. You can show this equation very easily. For example, if you look at the this equation where the peak deformation of the inelastic system divided by the peak deformation of the elastic system, uh, what you can do is to divide the numerator and denominator both by uy. Okay, u naught by uy, where um by uy will give you ductility, and u naught by uy, as we know from this, will give you r. So you can show even this way that the by u naught is equal to ductility divided by the yield reduction factor. Okay, now the equation of motion for a inelastic system. So we know that the general dynamic equation for a single degree of freedom system is mass time acceleration, damping uh, time velocity, plus the stiffness based force that is equal to the mass time the input acceleration. Okay? If you divide this equation by m, by the mass, you get acceleration here. Then this equation, we have the damping ratio now, the omega n times velocity, plus this term Fs divided by the mass is equal to minus u g. Now the force Fs in this case, we know that it is the function of velocity, the displacement, and also it depends on the sign of the velocity. Just right here. Okay? Because the force deformation relationship of the system is no longer linear. So it can be defined by not only by Fs is equal to Ku, but it is defined by Fs uh, depending on the displacement as well as the sign of U. So the force can be sometime increasing, sometimes it can be constant, sometimes it can be decreasing depending on the sign. Sometimes it's negative, sometimes it's positive. Okay. So as for linearly elastic system, numerical method for solving this equation are implemented in a number of computer program, and we already talked about this in the past lectures. But in case of the inelastic behavior, special attention must be given to the numerical procedure to detect the time instant accurately enough when the system transitions from an elastic to a yielding branch or vice versa. So for a given acceleration, let's say if the acceleration is given, which is the input acceleration, the displacement depends on three system parameters. Okay? So ut depends on the three system parameter, that is omega n, it depends on the damping, and it depends on the uy. While for the same ug, the ductility factor, it depends on omega n, it depends on the damping, as well as it depends on the strength reduction factor. Okay? And we will see that, and is also shown by the uh, past experimental test, that if you double the ground acceleration, the ductility factor is double. And there is also another way. If you use the same ground motion, but when you reduce the strength reduction factor by 2 times, again you have the same ductility demand. So you can get the same ductility demand either by doubling the ground motion or by reducing the strength reduction factor by twice. Now, regarding the peak deformation and ductility demand, the deformation response of an inelastic system that is defined by the initial elastic vibration period, damping ratio, and the force deformation relationship, and its corresponding linear system, of course, are determined by the numerical solutions. So whenever you are looking at the response of linear system, they are obtained by using the computer programs. The peak deformation and the peak deformation of this is for the inelastic, and the peak deformation for the elastic is u naught. So this is, let me just write here, this is inelastic, and this is elastic. So um and u naught are basically obtained from the response histories of the behavior. For example, you look at the displacement response of the system, okay, something like this, and then you pick that, okay, this is the peak deformation. So if it is elastic behavior, you get u naught. If it is inelastic behavior, you get um. So the ductility demand is then computed using the known yield strength, the known yield deformation for the system, or using RY. So once you know UM and U naught for a system, you can use this equation to obtain the ductility. Okay? Or you can use this equation UM by UI to obtain ductility. There are two ways to calculate ductility demand for a given system. Let me just show you an example. Okay, so what you see in this example figure, these are the plots of peak deformation of the UM and U naught of the inelastic system or the elastic system, and of the on the other side, these plots will be also shown in terms of the ductility. Okay, so let's talk about this. In these plots, you see that this plot is for the single earthquake ground motion, for the El Centro ground motion, and this plot is for a set of or ensemble of 20 ground motion records. There is written as LMSR, where LMSR represents the large magnitude and shorter distance ensemble of ground motion. So it's a set of ground motions that are basically selected for the large magnitude and uh, short distance between the site and the fault. Okay, and what you see here that the peak deformation demand is shown with respect to the natural vibration period, the Tn, okay, for various selected value of Ry. Okay, so if you understand what is happening here, okay, so an elastic system is taken where analysis is carried out to calculate U naught. That represents the Ry. Ry is equal to 1, okay, which means Ry, if you remember, is equal to F naught divided by F1. So they are both the same. It means the behavior is entirely elastic. But then the strength of the system is reduced 1.5. So this is the system strength. Then it is reduced by 2. So this is another system. It is reduced by 4 and it is reduced by 8. So these kind of reduction is carried out for strength in order to look at the peak deformation. And these are the peak deformation for various systems. Okay, the maximum displacement. In this plot, you can see that the peak deformation, they are normalized by the maximum ground displacement of the input ground motion. So this is for a single earthquake, and these are for the 20 ground motions. But you can see that every line is a median line. It shows the median value. When you have a set of a quantity, a set of values for a given quantity, so what you do is that you take the median. Sometimes we also take the mean, but it is better to take the median. Median is also called as the geometric mean, which is actually better than the mean only, which is the average. So the median is the one which is the 50th percentile. So which means that 50% of the data is less than that, 50% is more than that. Okay. So what you see here, in case of single earthquake, you can see that there are some jagged type of behavior, sometimes increasing, sometimes decreasing. But if you look at the behavior here, you can see that the response is now more smoother than the single ground motion. So that's why it's important to look at the a number of records rather than looking at just one record. Okay, you can also have a look at this plot, which is exactly the same data, but now it is represented in terms of the ductility rather than the peak deformation. Okay, and again, you can see that these values are shown for the same single degree of freedom system where the strength is reduced by 1 by a factor of 1, 1.5, 2, 4, and 8. Okay? So what you see from this plot, this as well as this one, is that for a system with the vibration period in the acceleration sensitive region, for example, let me just go here. Let's look at the TC. So we are looking at this here. When T naught is equal to Tc, you can see that the ratio, the um, this by ug or u naught by ug, the ratio for all these lines, it gets almost the same. Like I'm applying a different reduction factor, so I can see that the behavior is essentially the same. All of them are giving the same value regardless of how much strength is reduced. Okay. So whether the system behave elastically, whether the system behave inelastically, the displacement is the same. But if you look at this part here, to this part, in this part you can see that when I apply strength reduction, the peak deformation in comparison to this elastic deformation increases significantly, quite largely. Okay. For example, even if I look at this 1.5, just applying 1.5 strength reduction, there is a huge increase in the deformation, at least in a very short period. Okay, the same behavior can be also seen in terms of the ductility. For example, if I make Tn is equal to Tc, okay, so you will see that ductility is equal to almost the amount of strength reduction applied. I'm reducing Ry by 1.5, so I'm getting almost the same ductility, almost 1.5. 2, I'm getting almost ductility equal to 2. Okay, 4, 8, and so on. But if I look at this region here, where the time period, the vibration period is less than Tc. So in this time period, if we apply a given strength reduction, we can see that there's a huge difference in the ductility. So, for example, I'm applying a strength reduction of 1.5, but I'm getting a ductility of 20, 30, 40 in case of very, very short period systems, which shows that ductility is not exactly equal to a reduction factor, but it is equal to something else. Okay, but in the range, for example, in case of this range, okay, ductility is very much equal to the strength reduction applied. Okay, if it is in this region, if you see here, it's a displacement sensitive region. Okay, beyond the TF, this is also a displacement sensitive region, but in this case ductility is slightly lower than the strength reduction factor applied. Also in the velocity sensitive region, which is here, again ductility and strength reduction factor is exactly the same, and that's why in majority of the design and the assessment problem, when TC is when the vibration period is more than TC, if we are in this range, we always assume that ductility and uh, strength reduction factor, they are the same, which means that let me just draw here. For example, if you are in this range where the vibration period is more than Tc, we assume that for an elastic system, if we apply strength reduction, this deformation will be exactly the same. So U naught and UM will be exactly the same. This is what it tells us. And this kind of behavior is called as the equal displacement rule. Okay, so in majority of the design and assessment, this rule is used to convert values from the linear elastic system to an inelastic system. Now, the response spectrum for yield deformation and yield strength. Sorry, response spectrum. For yield deformation and yield strength. So we know that in designing a structure, one approach is to determine the yield strength. This can be Fy, not the yield strength reduction factor. Remember, this is Uy Fy. Fy. So when you are designing a structure, one approach is to determine the Fy. So for example, one approach will be to obtain yield strength in such a way to limit the ductility demand imposed by the ground motion to a specified allowable value. So you select this, okay, and then you look at the ductility. But this ductility should be, ideally, it should be equal to the allowable value, permissible value. Okay, how much ductility is present in your system. Okay, so it should be equal or it should be less than that. So in that case, you can design the structure confidently and without any issue. For example, if that particular earthquake will occur, the ductility demand on the system will be either equal to the ductility capacity or it will be equal less than that. So the structure behavior will be as per our own expectation. So in 1960, Newmark and Villetsos. So Newmark is quite famous and many people know him. So Newmark and his co-worker, they developed a response spectrum for the elastoplastic system. Okay, so they studied elastoplastic system. And the advantage of that spectrum is that it provides the desired information for the designer. These response spectrum, they were plotted for the value of dy is equal to the yield displacement of the structure. For the yield velocity, that is obtained using the pseudo relationship. In the yield acceleration, that is equal to the again to the displacement, convert it from the displacement using the pseudo relationship. Okay. Now in this equation, we assume that dy is equal to the yield displacement. Okay, so plots were developed. As such, the plot of dy with the ductility factor is called the yield deformation response spectrum. Okay, the quantity dy, vy, and ay, these were presented in a single four-way logarithmic plot. So a four-way logarithmic plot was used to plot ay, vy, and dy. Okay. The yield strength of an inelastic system necessary to limit its ductility demand to a selected ductility factor was obtained using the equation Fy is equal to Ay G into W. So that plot was used to obtain Ay, that was divided by G multiplied by the W, and the system designed for this yield strength was the one that will provide the system with a particular selected ductility. For example, there were a number of plots. Let me just show if we have. Okay, something like this. Okay, so either in a behavior like this, where the elastic spectrum was shown, showing Ay with respect to the with Tn, the natural vibration period, for a various value of ductility, ductility 1, 1.5, 2, 4, 8, and so on. Okay, so for any target ductility, you can knowing the initial or the natural vibration period of the system, you can go and select what AYG is required. What is the base shear coefficient that I need to design a system? How much strength I need in my system? Okay, or you can also look into the same in using this format of the design spectrum. It's a four-way logarithmic plot or a tripartite plot, and you can see that knowing the vibration period of the system and knowing the ductility for which you are designing, you can select the velocity Vy, you can select the displacement, and you can also select the acceleration Ay. So that Ay by G into W can be used to obtain the yield strength for your structure system. So those plots were obtained for the El Centro ground motion. And one you saw that it was a linear plot of AYG with respect to Tn, and the other was a four-way logarithmic plot that is showing all the dy, vy, ay value on one plot. Okay. When ductility is one, so it's obviously an elastic uh, response spectrum. Now let's look at the relationships, the RY, the strength reduction factor, ductility, and the vibration period, Tn. We know that the Fy for which we make a design is always less than the minimum strength, if not necessary, for the structure to remain elastic. So we all know that Fy is always less than F naught. And that's why the system behaves inelastically. Okay? And by this we mean that Ry is greater than 1. If Ry is 1, the strength reduction factor is 1 and the system will behave elastically. But when Ry is more than 1, the system will behave inelastically. We just show here. So what you see in this figure is that the yield strength is reduced with increasing value of the ductility factor. These are the same plots, but you can see that now these are shown for various ductility demand, ductility 1, 1.5, 2, 4, and 8. And what you see on the y-axis is the strength reduction factor uh, varying with time, with the vibration period, and the ductility. Okay, so if ductility is 1, you can see that Ry is 1 over all the vibration period value. But if ductility is 1.5, 2, 4, or 8, Ry changes accordingly. Okay. For example, even if you introduce a small ductility demand of 1.5, you can see that Ry changes to quite large values that from 1. Okay. And you can see that Ry increases with increasing ductility demand. So in case of the short period, somewhere here, Ry tends to be 1 in all cases, regardless of the vibration period. For example, if you are very close to 0.02 or even less than that, all these value will get equal to 1, no matter how much ductility demand is there. Okay? And in a very large value of vibration period, like here, Ry tends to ductility. So for example, if you are applying ductility 8, Ry is 8. If you are applying ductility 4, Ry is 4. Okay? But in this range, T8 to Te, there is variation. Okay? But the variation between Ta and Tb and Tc, they are more severe as compared to between Tc and Td and Td and Te or Tf. Okay? You can have a look that Ry in this case, for example, if you apply a ductility of 8, you can see R which is close to 3. So it is less than 8. Okay? But if you are in the vibration period in a range somewhere here, so sometime in this case, it is less than, for example, in case of 4, it's less than 4 and sometimes you are more than 4. Okay? Like in this case, more than 4, more than 4. And here it's 4. So this is for a single earthquake. If you look at the smooth behavior for a average of uh, 20 ground motion, in that case you can see a smooth behavior. So you can see that it's a constant value beyond the TF. It's 1 at a shorter period. It increases as the vibration period increases in this range. This is a steep change. Then you can see that the change is not that steep, and then it becomes quite mild. And at the very larger period, it get exactly the same. So reduction factor and ductility becomes the same. But you will see that in majority of uh, the computation for in codes or in the assessment guidelines, for the vibration period more than Tc, which is this one, this is considered as constant. Okay, and between this range, it is taken with some sort of slope, and there are certain relationship and equations available to obtain a relationship between the reduction factor as well as the ductility factor. So based on the results similar to these presented in the figure, several researcher has presented numerous equation, a very famous equation that by Newmark. Well, it shows Newmark in his group. We just write here. That has been used in a number of research. So Ry is equal to 1 when Tn, the vibration period of the structure, is less than Ta, and we just saw that. It is taken as equal to 2 mu minus 1 into square root when the Tn is greater than Tb and it is less than equal to Tc, but Tc prime. Okay, and when Tn is greater than Tc, it is taken equal to mu. Tc and Tc prime and Tc, they are related to each other. Uh, I think it is equal to Tc prime into Tc, 2 mu minus 1. But anyway, I will look at the exact equation of this. Let me just, anyway, this is, we will get the exact equation in the coming slides. Okay, so this was the famous relationships. Those were developed by Newmark and his co-worker. If you look how these plots, how these equations will look like in terms of plot, this is how it looked like. Okay, so if you are less than, having vibration period less than Ta, it's 1 between Ta and Tb. It's like a linear line defined by 2 mu minus 1 square root. And if you are between Tb and Tc, it becomes constant, then it changes with certain slope, okay, and then it reaches that R mu is equal to mu, that ductility. Remember that in equation we had that Tc prime and Tc, where Tc prime is this one. Okay? So this is actually the Tc, but the Tc prime is this one. If ductility is quite larger, Tc prime and Tc can be quite different. Okay, so with that same concept, using those equations of the Ry ductility and the Tn, the elastic design spectrum that was shown in the four-way plot can be shown as an inelastic one with this spectrum that is showing you the inelastic spectrum of the system for that known ductility. So you can see that this A branch is divided by 2 mu minus 1, which is the strength reduction factor. Okay, and in this range, the spectrum is divided by the mu, which is basically R, and there is in the velocity sensitive region, and again even in the displacement sensitive region, the displacement value R divided by mu, that represents the strength reduction factor. So these branches, 1, 2, 3, and 4, they are directly divided by the ductility, while this branch, they are divided by the 2 mu minus 1 to uh, to show the reduction factor at that location. So then it becomes the inelastic spectrum that you can use in the design or structure system if for a known ductility. Okay, now let's look at the constant ductility design spectrum. So I didn't mention here, but the plot that you just saw there is the constant ductility spectrum. When you divide those by the Ry, the various branches of the elastic spectrum. Structure designed for allowable ductility. So if we are given the design spectrum, the elastic spectrum, the structure properties like the vibration period, damping, and the allowable ductility factor. Okay, so we just mentioned here. The properties like the vibration period, damping, and the ductility factor. The design yield strength and design deformation for an SDF system can be determined from the inelastic design spectrum. If you have these, you can obtain what is the yield strength and you can obtain the design level deformation, UY, using the inelastic design spectrum that we just saw. So corresponding to how we do that, corresponding to the vibration period Tn, damping, and ductility, we can obtain AYG. Okay, that as you just saw, we can obtain that from the spectrum. If you know that AYG, you can obtain what is the yield strength of the design system. Okay, so this is the minimum yield strength necessary to limit the ductility demand to the allowable ductility factor on the system. So if you design for strength more than this, the ductility demand will be less than the allowable ductility. Okay, and if you design for less than this force, the ductility demand will be more than the allowable ductility, and that system may get severely damaged or can get collapse. For the inelastic system, it's also become important to compute the peak deformation of the inelastic system, which is the peak displacement is written by that is equal to the ductility times the uy, the yield displacement. And if the yield displacement is not known, you can multiply ductility by the omega, where omega by omega square. So in fact, divide by the omega. So it's the reciprocal of the omega into ay. Okay, because we know that uy is equal to ay into omega n square. So you can write that equation. If you know the natural vibration period, you can obtain the peak deformation of the single degree of freedom system. Alternatively, you can use the other equation for the because we know that is also equal to the ductility time uh, 1 over r u, and it is also equal to the Tn divided by 2 pi square into A, because this part is equal to the u naught. If you remember the equation that um divided by u naught is equal to ductility divided by r mu, ru, ry. So you can use either of these two equations to obtain the peak deformation of the inelastic system. So a system was designed to various ductility factor. So there was a single degree of freedom system. There is a natural vibration period equal to 1 second. The damping is 5 seconds. When this was subjected to ground motions for a number of ductility cases, taken is 8, 4, 2, and 1. So ductility 1 means that the system is essentially elastic. So the data that was obtained, let me just show it here, for ductility 1, 2, 4, and 8. So we can also show what is the yield strength of the system is a ratio of the weight of the system. So if it is elastic, it is equal to zero point 0.9 W. Okay. Uh, if you reduce by 2, it will become 0.45. If you reduce by 4, it becomes 0.225. It becomes 0.115 for 113 when the ductility is 8. So those are the target ductility. These are the yield strength of the system. If you take the ratio of the yield strength of the system with respect to the elastic force, it becomes 100%, which means that both are the same. It becomes 50%. This becomes one quarter, 25%, and this becomes 12.5%. 12.5. So in this system, these four different systems, when they were subjected to the ground motion, the peak displacement in inches were all equal to 8.8 inches. Okay, so all experiencing the same displacement demand. But of course, ductility is different. Okay, because we know that the if this is elastic, this is exactly getting the same displacement like this. This is 8.8 inches. This is Fs. Okay. So for 1, it is 8.8. For 1.5, it is 8.8. For 2, it is 8.8. For 4, and then for 8. But if you look at the ductility, because yield displacement is changing, so ductility is obviously different. Okay? In one case, ductility is 2, 4, and 8. And this yield strength is, this yield strength is 100%. This is by 1 by 2. This corresponds to 1/2 of the strength. This corresponds to 1/4 of the strength. And this corresponds to 1/8 of the strength. The last one is just like the steel moment frame or the SMRF that we use for the design. Now, these results indicate that if the structure is permitted to yield, its design force is reduced by the factor ductility, but the design deformation is unaffected. Okay, so ductility is affected, but the deformation is unaffected. You can see that both for the elastic as well as inelastic system, the deformation is the same. Okay, so if you are looking at the deformation control design, you can see that the amount of reduction is not causing any change in the deformation demand. And this is valid when the vibration period of the system is greater than the Karman period. For example, if you are in the spectra, in the velocity sensitive region or displacement sensitive region, these results, they are valid. So the practical implication of these results is that a structure may be designed for earthquake resistance by making it either very stronger or by making it very ductile. So you have the option either to select a less ductile system but very stronger because the strength is more, or you can say very highly ductile but with a very low strength. So you can select any combination, but it depends on what you can provide in the system. For example, if the system is a masonry system, so you cannot provide larger ductility, but you can provide very high strength. But if you are looking at ductile system like steel frames, you can provide quite larger ductility, and this will help you in selecting smaller strength. So you can select any combination for the design, but depending on the structure system and the material. But if you select the combination inadequate, for example, you are selecting larger ductility and the system is not ductile, it can have a problem. Okay. Okay, so I think I will take a break and we'll take a break of, I don't know, is it okay if we take a 30 minutes break or?
Yes, sir, 30 minutes.
ओके सो आप जा सकते हैं इसमें अगर आप कुछ लंच वगैरह करते हैं ठीक है नमाज पढ़ते हैं सो यू कैन डू इट प्लीज